Hello, my name is Nathan Farmer, and welcome to my presentation on our third lab, the magnetic field of a bar magnet. So in this lab, we pretty much had three objectives: to calculate the relationship between distance and strength of a magnetic field, to evaluate the magnetic dipole moment of our magnet, and then to experimentally compare the off-axis magnetic forces to some computational ones. While we're doing all this, though, some things we had to keep in mind were just magnetic dipoles, for instance, because we're comparing, a field strength to distance from it, and then magnetic superposition, as we're not just working with the bar magnet, but also the Earth's magnetic field. So the experimentation that we did was just to determine how changes in location between magnet and magnetometer affect the recorded magnetic fields. Before we do this, though, we need to cancel out the x-axis magnetic field by pointing it at the north magnetic pole, and then aligning two rulers perpendicular and parallel to the phone, and identifying an exact location of the magnetometer for more accurate recordings. Now that we move on to the experimenting, the first part of which is just changing the distance from a magnet to the phone and recording these distances that generate specific field strengths, plugging those into Excel. And then the second part consists of placing the phone at a set distance at a 45-degree off-axis angle, and then measuring the components of the magnetic field at that position. Of course, accounting for the Earth's magnetic field in the Y, now that we're just not doing on axis. So for the part one, what we end up needing to do is calculate the relationship between the distance and the field strength. And as we know, this is an exponential relationship, so in order to isolate that exponent, we need to take the logarithm of both sides. When we do this, we get this bottom equation here, which can actually be graphed to give us the slope of the line being that relationship. So when we do that, we get that the slope is negative 2.73, and this is very close to the theoretical assumption of negative 3. But now that we know the relationship between the distance and the field strength, we still need to know that magnetic dipole moment. And to do that, we know that the intercept of this is going to be the ln of k. So by rearranging some of our terms, we can get that the magnetic dipole moment is 4.549 amp square meters. For our second part of our experiment that we did with the off-axis recording, what I ended up getting was a dperp of 0.1791 meters, and then when I placed the magnetometer to the right this much and up this much, so 45 degrees off axis, these are the results that I get for the magnetic field here. The important thing to note here is that 2.34 e to the negative fifth Teslas is the overall magnetic field from this magnet. So now that we have this magnetic dipole moment and the experimentally determined field at that 45-degree off-axis, we want to compare it with a computational model. So all I have to do first is plug in that dipole moment and then use a function to or create a function to determine the magnetic field at any point around this magnet. So then I just create arrows determined by this function, their length and direction at different distances from it, and then I create one final arrow to represent that magnet 45 degrees off axis by just plugging in that dperp, the what I got from the experimental value, and then finally what I get is this model right here, where this purple arrow represents that off-axis recording. And as you can see here is that some important notes are that the orange arrows here are the largest, and then all of the same color arrows are the same size. And one thing that's very interesting is that the magenta arrow is not actually at a 45-degree angle. Also, something important to note is that the magnitude of this off-axis field computationally was about twice the size of the experimental results. Some things that might contribute to this were that there's possible interference from other magnetic fields, and there was a possible malfunctioning of my magnetometer when I brought the magnet a little bit too close, but after a while it seemed to go away. Some important afterthoughts though are, what if I didn't orient it to compensate for a magnetic north? This would just mean that I would have to compensate for it in each of my results. Whenever I recorded on-axis recordings, I would have to subtract the Earth's contribution. And then what if I were to stick two identical magnets together? This would just make the magnetic dipole increase, which would therefore make the distances I record increase as well. That is my presentation. Thank you so much for watching.